Hello everyone, my name is Bryan Maldonado. I am a research and development staff. Around half of the US residential buildings were built before the 1980s where energy codes were in place, making them quite inefficient. If we look at this, there is low or no thermal insulation around the envelope, contributing to high air leakage rates, which contribute to heat loss through the walls and high energy consumption for cooling or heating. In particularly, this affects around 50 million low-income households that have to spend a significant amount of their budget to pay energy bills. A novel proposal for approaching this retrofitting problem is to use Overclad prefabricated panels. This has the advantage of generating minimal occupancy disruption. It can also shorten construction time. Since the walls are not built in place, they are rather shipped from a prefabricated factory, and it has a huge potential for automation. Recent studies shows that the current retrofit rate at the US is around 2%. The blue line here shows a prediction all the way to 2050, showing that there will be still around 30 million low-income households that will have high energy burden. So we are targeting a 5-fold increase of this rate to have a retrofit target rate of 10% yearly, such that we can decrease this energy burden by 2050. So we estimate that by retrofitting around 64 million houses, in particularly low income, we can save around $17 million in energy savings per year. Looking at the business as usual scenario for installing prefabricated components, we can see in the picture of the right how installation crews use manual methods communicating with the crane operator or the cherry picker operator via walkie-talkie, not being very precise, hence having zero to no automation. New technology being developed at Oak Ridge National Lab aims to automate this type of installation processes using state-of-the-art technology and algorithms. We have a procedure of scanning the building using highly accurate LiDAR data to generate digital twins with as-built dimensions. The talk that I'm gonna give today is gonna present the algorithms for generating an automated panel layout design, which will going to provide the target panel position in the digital twin. Once the installation crew arrives with the panelized system, the installation can take place. The target panel position is stored in the digital twin, and we have a method to track the real-time position and orientation of the panel as it's being installed, thereby generating an installation error that can be communicated to the crew precisely in order to minimize as much as possible installation errors. Moreover, another talk is also going to describe how we can use cable-driven parallel robot in order to achieve this autonomously. However, the missing part here is the integration of all of these components. The first step is the integration with the wireframe generated by our automated point cloud building envelope segmentation algorithm. The facade is defined by the points of the convex hull of the facade, and the openings are defined by rectangular points of windows and doors. These points are then passed to the second step, which is the initialization procedure. Here, each facade of the building is going to be registered as a plane, and a discretization procedure is going to define a grid that represents the accuracy of the method. This grid can be defined based on the accuracy needed. Finally, the constraints are also defined here, and a very important step is that the user can define the constraints regarding the panel sizes and the number of panels that are available for retrofitting the building. This will depend on the pre-manufactured plan, and the optimization is trying to minimize the number of panels used or to also maximize the coverage. The next set of steps happen in sequence. First is the panel placement. It is done by the constraint satisfaction problem. Once the panel is in place, then its location is verified by the AC3 backtracking algorithm that basically is guaranteeing that the constraint is satisfied. If the constraint is not satisfied, then the feasible space where a panel can be placed is explored to replace the panel. Otherwise, the algorithm moves to the next panel. This process happens iteratively until the optimal solution is found. Here we can see the results of the algorithm. We have tested this into 6 different facades at 3 different resolutions: decimeter, centimeter, and millimeter. In general, the initialization takes very few time, and the backtracking algorithm to determine the constraint satisfaction problem is the one that takes the most. We can see here how the time increases rapidly, almost exponentially, as the resolution increases. The coverage could be a little misleading since this will depend on the availability of panels. We have restricted our search to a small number of panels and different panel sizes. You can see here on the last column the different number of panels that were used. Here you can see the results of the algorithm in 2 different versions. These are in general design philosophies for manufacturing the panel. If the panel can be cut and altered such that windows can be fit within the panel, then the problem can be solved in the light panel layout design, which is the right one. You can see here that the panels are being placed next to each other and window openings are carved into each panel. One important constraint here, however, is that we do not want the edge of the panel to be close to the edge of an opening, because this could generate air or water intrusion. A more complicated problem that requires using smaller panels is the heavy panel layout design, which is the left one. In this case, the assumption is that the panel manufacturer cannot alter the panel that is manufactured. In that case, you cannot carve windows or doors in the panels, and you need to use panels in order to fill only the wall surface and not the opening surface. So in summary, we're working on this end-to-end system that uses point cloud data to generate the digital twin that can automate the panel layout design and can autonomously install prefabricated panels. We have the proposed algorithm that can work in a centimeter level in under 3 hours, and in future work we're planning to have the millimeter level approach to have comparable time. We have some clues on how to accelerate this, especially using memorization, where the backtracking algorithm for checking the constraint satisfaction doesn't have to explore the entire feasible space but be more strategic how the panels are placed. We need to do this study with more panel sizes. It is unclear, for example, how this could work if one of the dimensions of the panel varies continuously. That is something interesting that we want to explore. But nonetheless, the approach presented can handle a different complexity of facades and presents multiple solutions depending on what the panel manufacturer wants. If it wants a heavy or light design, or if it wants to prioritize minimizing the number of panels or maximizing the coverage area. Thank you very much for your time, and if you have questions, feel free to contact me.